So 10.2 started introducing some two-way tables near the end, and we're going to go ahead and just do an entire section on two-way tables. So two-way tables are a table that displays data collected from a source that belongs to two different categories. So for example, if we were to ask a group of students if they were going to the junior-senior banquet, we are asking two different types of people, juniors and seniors, and we're going to exclude sophomores and freshmen for a second. And they only have two options. They're either attending or they're not attending. And they could have, done a third one for maybe a maybe category, but they decided not to, and that's okay. So we have displayed our data showing two different categories. And so the first thing we need to sort of highlight is the idea of the two-way table. But the other thing that we should definitely take note of is that our joint frequency is each entry inside of our table, okay? Each entry inside of our table. And then our marginal frequency, that's going to be in the margins, so whatever is over here, and then finally our total. So we can easily calculate this by adding downwards and across. So if we want to figure out the total people attending, we would add 42 plus 77, and we would get 119. If we were to calculate or add up how many are not attending, we would do 64 plus 37, which is 101. 42, if we wanted to figure out how many total juniors were asked, we would add 42 plus 64, which would be 106. So notice I was adding this way now. All right, and then if we wanted to ask ourselves how many seniors in total were surveyed, we would add again across, and we would get 114. So then easily we could figure out how many people in total were asked about the junior-senior banquet, and we can add downward and we can add across. It'll give us the same answer. And typically, I recommend doing it twice, just doing both, because if you do it incorrectly the first time, then you can easily figure out where, if you've made a mistake by adding side, the 119 and the 101, does that equal 106 plus 114? So it's just a way to double check yourself. So example 1 says to complete or create a two-way table. And 1.1a on the left-hand side says you randomly survey students about whether they are in favor of planting a community garden at school. Of the 96 boys surveyed, 61 are in favor. Of 88 girls surveyed, 17 are against. Okay, so we're going to create our two-way table. The first thing we need to do is we are distinguishing between boys and girls. And remember, we need our total. All right, and then we are asking about a community garden, and we are asking if they are for it, or if they support it, or if they are against it. So they said yes, or they said no. And then, of course, we still need our total. So I'm just adding just some lines to keep my numbers a little bit organized. Okay. So now that I'm done with that, I can fill in the pieces that I need. It says of the 96 boys, well, that's my total boys. So I'm going to put my 96 over here in my marginal frequency. They said that 61 of these boys are in favor. So I'll put 61 here. They were in favor. And of the 88 girls, 17 are against. All right, so now that I'm done with that, I can either add or subtract to fill in the rest of my information. And I'm going to go ahead and just erase all the extra. I don't need anything below or beside this. So I'm going to, first off, ask myself, well, how many people in total were surveyed? So I would say 96 plus 88 is going to equal 184. So I know 184 people were surveyed in total. And now I can say, well, I can look at this piece right here. I can say, well, I had 96 boys who were surveyed. 61 said that they supported it. So if I subtract those two numbers, well, then that's going to give me my piece in the center. So I'd say 35 were against. And I can double check that I did that correctly. 61 plus 35 does in fact equal 96. Okay, perfect. So then I can figure out how many people in total said no. 35 35 plus 17 is going to be 52. All right, and then finally I can figure out how many girls in total, or actually I already know how many girls in total were asked, but I can figure out how many are in support by subtracting 17, and I'll get 71. And again, just double check, 71 plus 17 is 88. Okay, so I know I did that correctly. And then finally, I can add downwards, 61 plus 71 is equal to 132. 132. All right, so this is our way of completing the two-way table, and it's the same thing over and over again. So again, we're going to do another one, 1.2a. You survey 171 males, 180 females at the Grand Central Station. Of those, 132 males and 151 females washed their hands after using public restrooms. Now, given the pandemic, everybody should be washing their hands, but obviously some people are nasty. So we're going to go ahead and we're going to have our males and females, and then our total. Okay. Those who wash, or actually I'll say those who wash is a yes, and those who do not wash is a no, and then we'll have our total. So I'm just setting up my table first, right off the bat, making sure I'm going to keep all my numbers nice and organized. Okay, so now that I have that, I'm going to plug in my information. 171 total males were surveyed, total of 180 females were surveyed, and of those, 132 males washed their hands. So I'm going to put that in the yes category, and 151 females said they washed their hands after using a public restroom. All right, now I'm just going to figure out what my missing pieces are. So I can do the easiest one first. I have these two, which I can add to get my marginal frequency. So 132 plus 151 is going to be equal to 283. Actually, 283. And then I'm going to add downward here, 171 plus 180 is going to be 351. All right, and now I can go this way and figure out 171 minus 132 is 39. 39. Do the same thing for the females. 180 minus 151 is going to equal 29. And then I can finally add downwards 39 plus 29 is equal to 68. All right, so I'm just going to double check that everything adds up to 351. So I already went downwards, but I'm just going to add sideways just to make sure I did this correctly. 283 plus 68 equals 351. So yes, I did do it correctly, and I did my entire table correctly because those two marginal frequencies added up to that total amount. All right, so I'm not going to do I'm not going to do example 1.2b, which is about the debate team. I'm going to let you guys do that on your own, but I am going to do the 1.1b, which is a started table for us. It's already started. We just have to fill in the final pieces. So in this one, I don't really have anything to add, but remember, we add downwards to get the 50. So I just have to subtract to figure out what am I missing at the top. And what I'm missing is 50 minus 10, which is 40. All right. Then I can go sideways. All right. Again, I'm adding whatever number this is, and it's going to equal that. So I can take 50 minus 38, and I will get 12. So this is going to be 12. So now I can just fill in the other pieces. This is going to be 6. 40 minus 6 is going to be 34. And 34 plus something equals 38, so that would be a 4 here. All right, so I filled that in. So even though my numbers were in slightly different places, because of the pieces that it gave me, I was able to find out all of the other entries. So the relative and conditional relative frequencies is taking our two-way table and finding the probability for each one. And it says ratio of frequencies. It's the same thing. So we're going to go ahead and just sort of copy down some of this. We have our juniors and seniors and our total. All right. And we have, and it's the same information as we had before. We have those who are attending and those who are not attending. And then again, we have our total. And because we're now finding the probability, remember everything should add up to 1, because we learned that in, I think it was 10-1, or maybe it was 10-2, but if you are adding everything up, you should have everything equaling to 1 when it comes to probability. So we'll double check at the end and make sure everything adds to 1. But how we do this is we take whatever frequency or whatever joint frequency we have in our table, and we divide it by our total. So we're just going to take that 220 and divide all of these numbers by 220. And when we do that, we're going to get a decimal, or a frequency or probability. So 42 divided by 220, and I'm going to round to 2 decimal places, 0.19. 77 divided by 220 is going to be 0.35. 119 divided by 220 is going to be 0.54. Now, we're going to pause for a second. Notice how beforehand, when we added up 42 plus 77, it equaled 119. And notice how over here in our frequency, 0.19 plus 0.35 is equal to 0.54. So we have the same idea. So instead of doing all 9 entries divided by 220, you can just do your joint frequencies right here in the middle, and you can ignore the marginal frequencies for a second and then just add up at the end. So we'll have 64 divided by 220, which is going to be 64 divided by 220, keep missing the 0. It's going to be 0.29, and 37 divided by 220, it's going to be 0.17. It's 168, which rounds to 17. So 0.29 plus 0.17 is going to equal 0.46, and then we can add across, all right? That is the 0.19 plus 0.29. That should be 48, 0.48. 0.35 plus 0.17 is 0.52. All right, and now we're going to just double check. We're going to add downwards, and we're going to add across, and we need to make sure that it adds up to 0, or to 1, excuse me. 0.48 plus 0.52 is equal to 1. And 0.54 plus 0.46 is equal to 1. So we did it correctly. So again, this is just finding the probability. That's really what all this is, the probability of each piece. And then we're going to be using that in finding the conditional relative frequency. And that is to help us, again, to find the probability of dependent events, which is what we learned in 10-2. So let's do a couple more, and we will be done. So these are the same problems from example 1.1, and instead of creating our joint frequency or our two-way table, we are going to create the relative frequency, which is the probability. So I'm not going to have a picture of it next to it. You can look on page 1 to see what we already did, and we are going to go ahead and do our boys, girls total, our yes, our no's, and our totals. Just going to copy all this down really fast. Okay? And now that we have that, we can go ahead and figure out our probability. So in this table, we had a total of 184 people that we asked. So I'm going to take all of my numbers and I'm going to divide it, or excuse me, I'm going to only take my joint frequency numbers and divide that by my total. So 61 divided by 184 is going to be approximately 0.33. Again, round to 2 decimal places. 71 divided by 184 is equal to 0.39. 35 divided by 184 is going to be 0.19. And then 17 divided by 184 is going to be 0.09. All right, so now I'm going to add sideways 0.33 plus 0.19 is 0.52. 0.39 plus 0.09 is 0.48. I'm going to add downwards. 0.33 plus 0.39 is going to be 0.72. 0.19 plus 0.09 is going to equal 0.28. And then I'm going to add both across and both downwards to make sure that I have a 100 or a 1 at the end. If I don't, then I made a mistake somewhere. So 0.72 plus 0.28 is equal to 1. So I'm good there. Erase that arrow. And then 0.52 plus 0.48, I did that already, and it is in fact 1. So I know that I did this correctly. We'll do one more just to make sure that we're 100% comfortable with this. If you look at the piece below, again, our table is blank. We already filled in the pieces we need. We had a total of 50 people in this particular case. So 34 divided by 50 is going to be 0.68. 4 divided by 50 is going to be 0.08. 6 divided by 50 is going to be 0.12. And then the next one is also 6, so that would be 0.12. All right, I'm going to add downwards. 0.68 plus 0.08 is going to be 0.76. Add downward for the next one, you should get 0.24. Add sideways, 0.68 plus 0.12 should be 0.8. And if you add sideways for the second row, you should get 0.2. We're going to add sideways and downwards to make sure we're going to get a 1. 0.8 plus 0.2 is 1. And 0.76 plus 0.24 is also 1. All right, so we did all of that correctly. Good for us. And that is our, again, this is not our two-way table. This is just our joint relative frequency, or the probability. And now we're going to use this particular these particular numbers to answer some conditional probabilities. So in this particular problem, example 3, it says find the conditional probabilities of the event. And it gives a description for part 3.1, and it says a satellite TV provider surveys customers in 3 cities. The surveys ask whether they would recommend the TV provider to a friend, and the results, given as joint relative frequencies, are shown in the two-way table. So they've already found the probability for us, which is great. I'm thrilled. So we have that. I'm going to go ahead and find my marginal. This is my joint information. I want to find my marginal information. So I'm just going to add downwards and sideways until I get my answers. All right, I went ahead and just did that on my own. Again, I just added downwards and sideways to get my marginal information. And now I'm going to go ahead and read part A. It says, what is the probability that a randomly selected customer who is located in Glendale will recommend the provider? So remember in 10-2, I said this is going to, for some reason in English, it's going to switch when we write it as a probability. Because remember, our information is the probability of B given that A has happened. So that's why we switch it. The second piece of information is our B information, which is why we have to put it first. So our first piece of information that is related to our table is somebody who's related or somebody who's located in Glendale. So I'll say the probability of being in Glendale, and I'll just represent that by GD, or actually, hold on, that's my A information, will recommend the provider. So that's my second piece of information, or my B events. So that would be my yes, given that they are in Glendale. So if I were to write the whole formula, and remember it's going to equal the probability of B and A over the probability of A. So I'm going to say the probability of yes and they live in Glendale over the probability that they live in Glendale. Okay? So now I'm going to go ahead and find my pieces of information. So I have yes, actually I'll extend it. I've got my yes information, and I've got my Glendale information. My numerator should be where my two circles intersect. So it should be 0.29 over, and then my total of my denominator. So my Glendale information, the total, is down here at the bottom, 0.34. So if I type that into my calculator, it's going to be approximately 0.853, or 85.3%. And that is my answer. So then part B says, what is the probability that a randomly selected customer who will not recommend the provider? Okay, so that's my A information. Not recommended is my A information. And the provider is located in Long Beach. It's my B information, okay? So it comes second. That's why it's my B information. So if I were to write my piece, it would be the probability of living in Long Beach given that they do not recommend it. So again, I'm going to go ahead and I'm going to erase all of this because I don't need it anymore. And I'm going to circle my pieces. They do not recommend it. They do not recommend. And they live in Long Beach. Okay, so my intersection needs to be my numerator, 0.04, over my total of my A information, which is no. So that would be 0.12. Actually, let me erase all that and that so it doesn't interfere later. Okay, so it would be, again, 0.04 over 0.12. And if I type that in the calculator, it's going to give me 0.3 repeating. And so if I did a percentage, it would be 33.3%. And that's my answer. The final piece is really, it's a good way to apply practical information. It says, determine whether recommending the provider to a friend and living in Long Beach are independent events. So if they're independent, that means each event, obviously they do not affect each other, but equation or within mathematics, they would be approximately equivalent. So I'm going to use sort of this formula that I have over here, and my question is, and I'm not going to use all of it, I'm going to use some of it. I'm going to use the idea of the probability of B given A should be approximately equal to the probability of B. Okay? So this is to find the approximation of if they're independent or not. If they are equivalent, then they're independent. But if they are not, then it is not independent. And I won't say dependent just because there could be extenuating circumstances that we don't know about. Statistics can be very complicated, so we're just going to say it's not independent. All right, so let's go ahead and get started. Again, our first piece of information is about recommending. That's our A. And the next piece they gave us is that they live in Long Beach. So if I write it, it should be the probability of living in Long Beach given that they recommend it should be approximate to the probability that they live in Long Beach. So now I'm going to plug in my info. All right, my Long Beach, given that they recommend it, that should be the intersection of those pieces of information. So here's my Long Beach, here's my recommendation. That is going to be 0.32 over the total of my yes statement, which is 0.88. So there we go, 0.32 over 0.88. Again, that's how we find our probability of conditional information, okay? So it should be approximately equal to the probability of those who live in Long Beach. Well, there's a total of 0.36 in Long Beach. All right, and I don't have to do anything else with that because it's not conditional probability, so I don't have to put it over anything. So then I'm going to take my calculator, 0.32 divided by 0.88, and if I do that, it's going to give me 0.36 repeating. And so they are approximately equal to each other, so I would say yes, they are independent events. All right, and so let's do our next one, letter A for example 3.2. It says a store surveys customers of different ages. The survey asks whether they would like to see the store expanded in its toy department, and the results given as joint relative frequencies are shown in the two-way table. So we have our information, and it tells us that our columns are based off of ages in years. So we have those who are less than 10, those who are between 18 and 10, and those who are between 10 and 20, and then those who are greater than 20. All right, so again, I'm just going to add my marginal joint frequencies, my marginal relative frequencies. And then part A says, what is the probability that a randomly selected customer whose age is between 10 and 20, so that's my A event, would not like to see the toy department expanded? So we'd say the probability of saying no, given that they are between 10 and 20. So if I were to circle both columns, no, and between 10 and 20. Again, my overlapping circles is my numerator, 0.17, over my A events total, which is between 10 and 20. So that's going to be 0.23. Plug that into a calculator, and you should get 0.739 as a decimal, or 73.9%. All right. Letter B, what is the probability that a randomly selected customer who would like to see the toy department expanded, that's my A, is younger than 10, that's my B. So I would say the probability of being younger than 10 given that they said yes. Okay? So I'm actually gonna highlight it this time just so we can see the difference. Less than 10, and they said yes. Okay, overlapping information is going to be that 0.27 over the total of my A event, which is yes, which is going to be 0.56. So plug that into the calculator, and you should get 0.482, or 48.2%. Finally, determine whether replying yes, which is my A event, and being younger than 10, that's my B, are independent events. Okay, so I'm going to use the same idea. I'm going to say, well, if they are independent, then they should be approximately equal to just the probability of B, right? Because the probability of B would be our second event with no effect from our first event. So we would say the probability of being younger than 10, given that they said yes, is going to be approximately equal to the probability of being less than 10. So our probability of being less than 10, given that they said yes, okay, that is going to be something, we actually did that in part B, so I'm just going to copy that down. It should be 0.428, should be approximately equal to the probability of being less than 10. So that is my total of being less than 10, which is 0.36. And they do not equal. They are not approximately equal to each other. So we would say that no, these are not independent events. Our final example, example 4, is going to require us to create our own relative frequency table. And so I'm just going to go ahead and do that pretty quickly. But basically all I'm doing is I'm counting up how many tick marks I have. And in example 1, or A, 4.1, we have 50 total tick marks. And I'm going to read the problem to you for a second. It says a jogger wants to burn a certain number of calories during his workout. He maps out 3 possible jogging routes. Before each workout, he randomly selects a route and then determines the number of calories he burns and whether he reached his goal or not. The table shows his findings. Which route should he use? So again, we're going to create our relative frequency table, and that's going to be the one with the probability and stuff, and then we are going to figure out all of our pieces. So I'm just going to pause it really fast and just do it on my own so that you can so I don't waste your time really. So again, how I got all of these numbers is I took the tally marks in each cell. So like route A, where he reached his goal, he had a total of 11, and I divided it by the total. So like 11 divided by 50 is 0.22. So I just wanted to show that to you really, really fast. That's how I got all these values. But now that I'm done with that, I'm going to go ahead and figure out the probabilities of each route. Okay, so remember his goal is to burn an X number of calories. And so we want to know, well, what is the probability of reaching his goal? So saying yes. What is the probability of him reaching his goal given the route he took? So we're going to do each route. Probability of reaching his goal given the A route, probability of reaching his goal given the B route, and the probability of reaching his goal given the C route. And then we're going to compare the three and ask ourselves which one is going to get him to his goal most often. All right, so in our first probability, we need the probability of reaching his goal and being in route A, which is 0.22, over his total A route, which is 0.34. Divide this and you should get 0.647. All right, then we go to our B route. So we want to find yes and B, which is 0.22 again, over the total B route, which is 0.30, or actually 0.3, but whatever. And that is approximately 0.73 repeating. Given our C route, all right, yes and C is going to be 0.24 over our total C, which is 0.36, which is going to be approximately 0.6 repeating. All right, so now I can look at these three routes, and the corresponding, or the probability that I found, is the probability of being successful, okay, of reaching his goal given the route. So when he takes route A, he only has a 64.7% chance of reaching his goal. When he takes route B, he has a 73% chance of reaching his goal. And when he does route C, he has a 66.6% chance of reaching his goal. So we can see that the most reliable route is route B. So we would say our answer is route B. Route B. And why is that? Because he has a higher chance of reaching his goal with this route, of reaching his goal with this route. And this is our final answer. And really, we don't have to put the reason. I'm just adding that piece to you for you guys so that you understand why I picked route B. Technically, you only have to write what route it is, just so you know. All right, so we're going to do our last one just to make sure that we are understanding each piece. The 4.2 example says an airline company strives not to lose luggage for passengers. A manager at the company randomly selects 3 flights to check on lost luggage. At the end of each day, the manager determines whether or not there was luggage lost on the flight that day. The table shows the findings. Which flights does the best at not losing luggage? So again, we need our relative frequency table, so I'm going to go ahead and do that really fast. So I rounded this one to 3 decimals only because when I did it the first time and I rounded to 2, when I started adding our margins to get 1, it wasn't working because I had rounded too much in our joint information. So I just wanted to throw that out, why I did that. Typically, you just need to round by 2 and you should be good to go. But now that we have our relative frequency table, we can go ahead and figure out our probabilities. So the question with this problem is, which flight does the best at not losing luggage? And so we are going to go ahead and take each piece, find the probability. So we'll find the probability. I'll change the color. Probability of not getting lost given flight 1, probability of not losing luggage given flight 2, and the probability of not losing luggage given flight 3. Okay, so now that we have all of the pieces that we need, we're going to go ahead and find each piece. Not and 1 is going to be 0.075 over our total flight 1s, which is 0.325. Plug that in the calculator, and you should get approximately 0.231. Not losing luggage given flight 2 is going to be 0.125 over our total information for flight 2, which is 0.35, which is going to be approximately 0.357. And then finally, our last one is going to be 0.025 over our total flight 3 information, which is 0.325. That is going to be approximately 0.077. So again, we're looking for the flight that has the higher chance, or the highest chance of not losing our luggage. And it looks like flight number 2 is going to be the highest chance. With flight 1, we only have a 23% chance. With flight 3, we only have a 7% chance. But flight 2 has a 35, almost 36% chance of not losing any luggage. So we would say flight 2. And then if you wanted to put the description would be because it has the highest chance of not losing any luggage. All right, so that is how you do section 10-3. I hope it was helpful. If you have any questions, please make sure you reach out to me, and have a great day.